So you don't want anything that is reflective on your hands, not even a watch, because otherwise you might have reflections that you are not controlling, and it can be dangerous. Okay. Right now, as I said, this one is not an hazard, but in general, it's very important that you work in a safe way. Let's take our cylindrical lens. So I'll show you this one. So this is a cylindrical lens. Maybe you can have a look. So you see, it's I don't know if you can see what I want you to see, but here it's flat. Okay. This side, can you see that it's like a cylinder? All the efforts, can you see that it's curved only in one direction?
Yeah,
you can see, right? Okay, it should be quite obvious. Can you see? So, the thing is also, you would say, well, just clean it. It's not that easy to clean it, huh? You need the cleaning tools and then specific products. And sometimes some of the optics have coatings that you can damage if you clean. Okay, so for example, if you have a dielectric mirror, like the one that we were talking about today, when the other lady that was talking about compression with the dichroic mirrors, with the multi-layered mirrors, those mirrors are really expensive. You don't want to get them, like, you don't want to touch them. You just stay away from my dichroic mirror. And if you try to clean them, you might ruin the compression of your pulses, so it's really something that you shouldn't do. Well, now it's done. Yeah, exactly. So I'll show you. So if I mount here this lens, okay, this mounting that I have placed here, it is a mounting that can rotate. Okay, so let's see what happens. Okay, first of all, let's check with a piece of paper, so we check in a controlled way. So I'm here, I'm very close to the lens, and there is nothing to see. But if I go in the focal plane, look, I have a line. Mm-hmm. Can you see? Yes. So the focal plane of this lens, it's a spot, it's a single dot. Mm-hmm. Here, the focal plane, it's a line. Okay? Mm-hmm. Why is that vertical? Here it was round, here it's round. Here it's horizontal, and over there is vertical. First of all, if we think of this in 3D, it's a plane. Look, you can see the plane if I do this. Can you see that it's a plane?
Yeah.
Okay. If I rotate the cylindrical lens, so I'm rotating it, you can see I can rotate the beam.
Yes.
Okay, now it's vertical. If I do like this, you can see even better, probably that this is a plane. Yeah. Can you see? Okay, in the other direction now. Okay, so if I rotate while I move, you can see it nicely. I have a trick. If I have time, I will show you my trick. My trick is use, I'll show you later. It's a nice trick though, so I want to show you. Let's go on. How large it is here in the focus? Somebody can read?
About 0.8.
Yeah, are you sure?
Yeah.
Okay, so then you tell me.
End.
Okay, so how large was it here?
0.7.
No, then it has to be the same. Because what the cylindrical lens does, it squeezes in one direction, but the other one is left untouched. So the height of the beam, it's the same. Because it doesn't do anything in one of the two directions. So now let's look at the propagation. What do you think is the thickness here? It's 0.7. Do you want to check? Want to come and check? So you have to say that is 7. Huh? It's 7.
Yeah, it is 0.7.
Yeah, it's 7. Otherwise, physics doesn't work. This is a 10x objective. It will magnify 10 times, and it has a 0.28 numerical aperture. Do you think this is a large number or not? It's not. It's not. A good 10x is 0.4 usually. At least 0.3, come on, this is 0.28. Why? Well, this objective has the pro, it has a good point of being long working distance. So the focal length, it's very long, so this gives me the opportunity to mount in a three-dimensional manner my sample. So I have space. I don't need to stay here very close to the objective. I can have something that is very big. If my sample is 1 centimeter, I need to be able to move it around, for example. So I want to have room. If I was using a very high NA objective, I would have a better resolution, but good resolution is not everything. Because maybe you want to see a large field of view, which is usually what I want to do. Larger field of view. Anyway, so what we will do today, I told you that the objective has many lenses inside. Yeah. Why?
Chromatic aberration.
Exactly. So all those lenses are needed, okay, to have the right magnification, to collect as much light as possible, and to correct aberrations. In particular, chromatic aberrations. So this is a plan apo objective. Apo stands for apochromatic. It means that it's corrected for a broad range of wavelengths. Still, if after this I put a lens that is not corrected chromatically, I mean, this is useless, right? So this one is not a single lens, it's not a thin lens, it's not a single one, it is a triplet. It's probably at least a triplet, meaning that it's at least 2 or 3 lenses all together, put all together, so that chromatic aberrations are corrected. Okay? So we will have to put this, the tube lens, after, okay? And then the camera. This objective, we will put at the focal point from the plane. Okay? Then after this, which we can imagine it's just a single lens, what happens to the light? I told you already what is going on after the objective. It's collimated. Okay. So where should I put this lens? Does it really matter? And the factory who makes this tool, makes this, tells you, because otherwise, well, you could experimentally find it, but it's easier to check online. So, and I can tell you that the right range is from 7 to 17 centimeters. And what you will see is, as an effect, you will start cutting some of the frequencies of your light, and you will have an effect of vignetting. Good, all good, all good. Okay. Okay, so there is a mirror mounted inside here. Okay, now I don't care, I'm not going to attach it. So do you remember what I asked you today? So what I told you today? So if we have a beam that hits a mirror, okay, so that's it, fine. So what happens if I rotate the mirror now? This is a lens of 50 millimeters focal length. So over there, it's really divergent. So my question is, what happens if I rotate the mirror now with the lens in front of it? Who knows the answer?
I can try.
Yeah, please.
As you rotate, it's going to converge until you have now a more precise beam.
No. That's not what I wanted to hear. Okay, this rotation, when you go to when you use a lens in front, will become, go closer please to my hand, yeah, perfect. And now start moving very quickly, okay? Quicker. Means that if I rotate this mirror at the focal plane of my objective, I will be able to rigidly translate the light sheet. So this is why I want to have these 2 mirrors and these 2 lenses, to have a degree of freedom to position with a micrometric precision my light sheet, okay? Because we said we have to position it so that it matches the the focal plane of the detection objective. Let's see what happens. I will do the drawing again. We don't need the first mirror anymore. So here we have a lens. Here we have our objective. So a rotation here makes a translation there. And at the focal plane, we will have a rotation. So I will be able to rotate the light sheet, okay? So that if the light sheet is tilted, if it is at an angle, I can compensate for that by rotating the mirror. And I can do that both for the horizontal plane and the vertical plane.
One of the lenses we are going to, when you are rotating,
Yes.
we are going to translate. Those lenses, are they the same? Are they of the same focal length?
This one, they will be the same focal length,
So
okay?
Is the second one going to cancel the translation of the first one?
No. If actually you need both, otherwise it would not work.
Yeah.
Yes.
And then this translation will be reflected on this lens.
Yes. So what does this lens do? The angular displacement that you have here, the rotation here, will be is the same at this lens.
Oh, I understand.
Okay.
Oh, thank you.
Any other question? So this system is collimated in one direction, but in the other one, it's not. Okay, it's focusing here. We have to remember this. Next time, I hope that we will have some good image, not just beams.
Thank
All
you.
right.
Thank you.
See you tomorrow. Have a nice night.